Good morning, everybody. Today we're going to be talking about valence shell electron pair repulsion. Now, just like the name implies, we're going to be looking at valence shell electron pair repulsion, VSEPR, V-S-E-P-R. Okay? What this unit talks about is how the molecules take their shapes, right? Why do they have the shapes that they have? And the concept that forces the shapes are actually very, very simple. Okay? We just got done talking about covalent Lewis dot bonding, right? We figured out that when you have a covalent bond, the elements are sharing their electrons, right? So let me give you an example here. Now, if I drew an oxygen here, right, and he's going to bond with two hydrogens, okay? He's going to bond with two hydrogens. I'm going to draw this generically here, right here. Right? He's going to bond with two hydrogens. Well, what's happening is they're sharing electrons, right? Now, hydrogen ends up, or oxygen ends up with all of his electrons that he wants, so he's happy. And hydrogen ends up with his electrons, so he's happy. Everybody's happy, right? Now, these guys have this big negative, right? Everybody's negative. Now, if you have negative, 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 everybody's the same thing, what do likes do? We know what opposites do. What does opposites do? Opposites attract, right? So when you have two things that are not opposite, they're the same, what do you think they do? They repel one another, right? So we're sitting here with two guys with a bunch of negativeness, another guy with a bunch of negativeness, and they don't want to be around each other, right? They want to get away from each other and repel, right? So essentially, that's what's happening here. When we talk about VSEPR, we're talking about everybody's happy. Everybody has their electrons and everybody's fundamentally negative, right? So all the molecules or all the elements are trying to get away from each other because everybody's negative. Well, in the case of water, you would suspect that it would look something like this molecule, linear, right? This is because it's straight, linear. Well, with oxygen, he has this set of paired unshared electrons sitting over here, right? And these guys will also exert a force. Boom, 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 boom. This big old negative force sitting here, and it's another negative force, boom, 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 boom. This is a big old negative force. So if we have these two giant negative forces, everybody wants to repel. Everybody, they even want to get away from these giant negative forces here, right? They want to get away. So that's exactly what they do. You end up with this guy looking right here. We have hydrogen, and these two, the oxygen and the two hydrogens, want to get away from each other because of these big negative guys, right? Now, essentially what's happening is these two paired unshared electrons exert a force as if there were two other things bonded here, right? But the only reason why they're moving is because everybody is negative and everybody wants to get away from each other, right? So I know it's hard to understand looking at 2D. So what I'm going to do is I'm going to make a video, show you a video of this in action, but from a 3D standpoint, using a 3D model, okay? But all you have to remember is they're all trying to get away from each other because they're happy, their last shell is full, they're all negative, and they want to repel each other. So they take their shapes because they're all trying to get as far away from each other as possible. Okay? So let's go ahead and start that video now. Okay, so this morning I'm going to go over VSEPR, valence shell electron pair repulsion. And what's really happening here is I'm using kind of like this 3D model to explain to you how the molecules take their shapes and why they take them, okay? So we're going to be looking at this right here. This is going to be our central atom. It's the big one. And then we're going to be putting a bunch of little satellite atoms around it, okay? So we got our big atom, which is our central atom, and our little atoms. Now, what we're talking about here are the shapes of the molecules. And there's 6 shapes you need to know for this unit: linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral, okay? So these are the ones you have to know. But it's really simple, guys. Remember what I said before. When they share their electrons, they get wrapped around with 8 electrons in their outer shell. He has 8 electrons. Everybody has 8 electrons, right? We know these electrons have negative charges. So because of that, when we have two guys who's full of electrons and who are happy, they don't want to be by each other. It's negative, negative. So what do two opposite things do? They repel one another, right? And because of this repulsive force, they go to move as far away from each other as possible, okay? And that's what dictates the shape of molecules. It's really just all the satellite atoms trying to get away from each other, okay? So let's go over a couple shapes here. Well, if I just take my atom, right, and I put in just one bond, right? This is what our molecule is going to look like. The only shape this takes is linear. It's straight, right? No matter how you look at it in the 3D model, it's linear, okay? So that one's simple. But what if I was to bond another atom to it, right? Well, there's only really one rule. They have to be as far away from each other as possible. So where could I put this other one in here to where it's the furthest away? Remember, I'm working in this 3D world here, so I can put it anywhere, but what is the furthest away? Well, let's see. I think way on the other side is the furthest way we can put it, right? So it looks like this, okay? Now, honestly, if I was to move this bond anywhere else, it would be getting closer, okay? If I was to move it anywhere else, it would be getting closer. Okay, so this is still linear. You can see that it's still linear. Okay, now what's next is, what if I make a third bond? Okay, a third bond. So I'm going to have to change some stuff around. I'm going to have to take these guys out, because if I was to make a third bond, these guys are going to move because of the third one's coming in. Okay. I think that's it right there. Boom. If I was to put a third one in there, they would all shift around. This third one would push the other two down, okay? The third one pushes the other two down. This one is called trigonal planar, right? Trigonal means 3, 1, 2, 3, and they're all in the same plane. Like if we were to put a piece of paper here, they're all in the same plane. None is bumping up or down outside of the plane. They're all three in the same plane, okay? Now, elements, if you go to look at the periodic table, look at the elements in group 13. The group 13 elements all would make this shape right here, okay? They all have an oxidation number of 3, 6, 5, 4, 3, and they all have 3 valence electrons, right? So they're going to be bonding 3 times. This is it right here. Now, what if I was to put a 4th atom on here? Now, group 14 makes 4 bonds, right? It's that plus or minus 4 group, and they make 4 bonds. But what if I was to stick another bond on here? What do you think is going to happen, right? So let's do some rearranging, because it's going to require some rearranging here. Or maybe I could just go like this. Okay. Boom. Okay, good. Now what we have here is, everybody see this shape right here? Looks the same no matter how you do it. Uh-oh, my clay is getting weak. Okay. These are bent down a little bit. This is what you call a tetrahedral, okay? This is what you call a tetrahedral. Now my 3 trigonal planars, because I put this top one in here, are bending the other 3 down because they're trying to get away from each other. So I have my tetrahedral here now. Remember, if we skip over one more element, let me give you an example. Let me set this down real quick. If we look at nitrogen here, this is nitrogen. He has 5 valence electrons, and he has right here 1, 2, 3, 4, 5. He has this set of paired unshared electrons here, right? Well, these guys, remember, they're not doing anything, but they do exert a negative force as if something was there, right? And this negative force is going to push these guys, if something was bonded to it, out of the way, right? So now we're looking at group 15 elements like nitrogen on down, right? They have this set of paired unshared. So what's really happening here, here's my tetrahedral with carbon, right? So we got our 4, but we can go like this. Let's take this element off, and now in real life, you wouldn't be able to see this stick right here because this represents a paired unshared electrons. And that paired unshared exerts a force as if there was a 4th element there, still pushing the other 3 down, okay? So this would be like group 13, nitrogen and all that, okay? You have this set of paired unshared electrons. Nothing's there, but the force of the 2 negative electrons are pushing the other 3 down, okay? Now, let's go to group 16, the oxygen group. If you go oxygen and down, they all look like this. They have 6 valence electrons, and look what they have. They have 2 sets of paired unshared electrons. And remember, these paired unshared electrons, they don't bond, but they do exert this big old negative force right here that acts like something is bonded there. So what it's going to do is push these 2 bonds out of the way, okay? But we have these 2 sets of paired unshared electrons. So if we look at my model here, it would look something like this. This is nitrogen, 1 set of paired unshared, but let me take off another one. And now look, we have 2 sets of paired unshared electrons, and what is it doing? It's bending the other 2 down, just like if we had 4 things bonded. So the other one, when it was just 3, right? When it was 3, this one is called pyramidal, because if we connect it, it looks like a pyramid, right? And if we take off the other one, now it just looks like this. And this is what we call bent, because it should be linear, but now it's bent because of these 2 paired unshared electrons, okay? So now we're going to add another one, okay? We're going to add another one, and this time we're going to have 5 things bonded. And you know how, put this back on, put this back on. This top guy is bending these 3 down. Well, if I add another one, what's going to happen? Oops, pushing it too far. If I add another one, his presence is actually going to bend those 3 that were bent down back up, okay? Those 3 that were bent down are now going to be bent back up. So his force is pushing these guys back up, even though his force is pushing this way, his force is pushing that way, and we end up with a molecule that looks something like this, okay? Everything is symmetrical, everything is good. Everybody see that? These 3 are back inside the plane, these 2 are straight up, okay? So this one is called trigonal bipyramidal. Trigonal bipyramidal. Everything is nice and straight. Everybody can see that. Now, what if I stuck finally a last one in here, okay? So what's going to happen, it's going to look something like this. Let me rearrange this guy. Everybody has to be straight. And I think that's a close approximation. If I stuck in one more guy, it would look something like this. We have 4 that are in the plane together, right? So it looks like this. So this is the shape. Every time you bond one more, it changes the shape, but they all have one goal: to get as far away from each other as possible because they're repelling one another, okay? They're repelling one another because they have full octets, so they're surrounded by these negative electrons, and they're nice and happy, and they want to get away from each other because of repulsion. All sharing electrons, all becoming happy because they all have a full octet, 8 electrons in their outer shell. In the case of hydrogen and helium, only 2. Okay, so guys, this one is called an octahedral. Okay, if I was to connect all the dots and lines and stuff, we would have 4 sides, 1, 2, 3, 4, and then another 4, 1, 2, 3, 4, giving me a total of 8 sides. Octa means 8, octahedral. So if I connected all the lines, it would be 8 sides on this guy. Okay, and guys, this is molecules through VSEPR, valence shell electron pair repulsion, and I hope this helps you visualize what these guys are looking like and why they look that way. Okay, welcome back. So you just watched that video of me showing you the 3D models and how and why they take their shapes, right? Now, what I have here is just a breakdown, guys. This is like a recap, the notes that you'll probably need to use to get you through this unit, okay? So we talked about linear, right? When 2 things are bonded together, and then when we put a third one on here, or actually 2 guys bonded to a central atom, we're still linear. But what if we add a third atom to the central atom, just like the group 3 elements, right? They take this shape, trigonal planar, right? They're all trying to get as far away from each other as possible. And then we talked about the tetrahedral, right? 4 things bonded. They're all moving to get as far away from each other as possible. These 3 were in the same plane, but when we plop another one on there, it pushes those 3 down into the plane, okay? And then we talked about our group 15 elements, right? Our group 15, like nitrogen, phosphorus, those guys, they have this set of paired unshared electrons. Remember, that acts as if there was a 4th element there. It exerts this negative force that keeps those 3 bent so they don't go back up to the trigonal planars. So they end up being what they call pyramidal, okay, because of this set of paired unshared. But what if we have 2 sets of paired unshared, right? Like the oxygen-sulfur group, group 16, right? They create a bent look, a bent conformation. See, it's bent. So these 2 paired unshared are acting like 2 elements in here, right? So these 3 are part of the tetrahedral family, but this one is called pyramidal because you wouldn't be able to see the paired unshared, but there is a force there. And if you had to like draw the picture, it looks like a pyramid. And this one's just bent, boom, boom, just like that, right? Because if you had just 2, shouldn't it be linear like this guy? Well, he doesn't have a set of paired unshared, so it is linear. But when you get those sets of paired unshared, it causes the molecule to bend as if there were elements there, okay? Now, if we move up a little bit, right here, this is if we had 5 elements attached. Now remember, with tetrahedral, we had 4, right? By adding this guy, it bent these 3 down, okay? Now, if we put one on the bottom, what it's going to do is push those 3 that were bent down back up into the plane. So now we have 2 guys top, bottom, and these 3 guys in the plane. And that one's called trigonal bipyramidal. And finally, our octahedral, we just add another one. They take like this X conformation, trying to get as far away from each other as possible, and these guys stay up and down, okay? And guys, this is valence shell electron pair repulsion. I hope this helps you, and I hope you understand why these molecules take these shapes. It's only because they are all happy, they have all their electrons, and they're trying to get as far away from each other as possible. Guys, VSEPR, have a great day.